For decades, scientists have been haunted by a paradox on Saturn's largest moon, Titan. Its thick methane atmosphere, a key ingredient for its Earth-like features, should have vanished eons ago, broken down by sunlight. Something is replenishing it, but the source remained a complete mystery. That is, until NASA's Cassini spacecraft detected something bizarre deep beneath Titan's icy surface. A discovery that could rewrite the rules for where we look for life in the universe. Titan isn't just any moon. It's the second largest in our solar system, even bigger than the planet Mercury. And unlike any other moon we know, it boasts a dense, planet-like atmosphere, making it a truly unique celestial body. This atmosphere is mostly nitrogen, about 94.2%, with a significant amount of methane, around 5.65%, and trace amounts of other hydrocarbons. The surface pressure on Titan is surprisingly high, about 1.5 times what we experience at sea level here on Earth, equivalent to diving 50 feet deep in our oceans. At a frigid -179 degrees Celsius, this pressure allows methane to exist not just as a gas, but also as a liquid, forming rivers, lakes, and even vast seas. Picture this. You're standing on the shore of a lake so vast it curls over the horizon. But the water isn't water at all. It's liquid methane, -179 degrees Celsius, lapping at a beach of frozen benzene. Above you, an orange haze hangs so thick it blots out the rings of Saturn. This is Titan, and the single biggest question about this alien world is deceptively simple. Why does it still have air? Methane in Titan's upper atmosphere is constantly shredded by ultraviolet sunlight. The math is brutal. Every photon breaks a molecule. Every broken molecule drifts away or rains down as tar. Add it up, and the entire atmospheric supply should be gone in, at most, 30 million years. That sounds like a long time, until you realize Titan itself is 4 billion years old. Do the division. The methane should have run out 100 times over. Yet the lakes are still full. The clouds still roll in. The weather forecast is still chance of methane drizzle. Something, somewhere, is topping up the tank. For planetary scientists, that something became the most annoying loose end in the outer solar system. These aren't just puddles either. Titan's surface is dotted with immense seas and lakes of liquid hydrocarbons, primarily methane and ethane, concentrated near its north pole. In fact, over 1.6 million square kilometers of Titan's surface are covered by these liquids. That's more than all of Earth's oil reserves combined. The largest of these, Kraken Mare, is truly colossal, spanning over 500,000 square kilometers, making it larger than Earth's Caspian Sea and roughly the size of all 5 Great Lakes combined. It's also incredibly deep, estimated to be at least 100 meters and likely over 300 meters in places, with some areas too deep for Cassini's radar to even touch bottom. What's truly fascinating is how Titan's methane cycle mirrors Earth's water cycle. Methane evaporates, forms clouds, rains down, and carves river channels and deltas across the landscape. The Huygens probe, which made a historic landing on Titan in 2005, even captured images of these drainage channels and rounded ice boulders sculpted by liquid erosion, revealing a dynamic yet alien geology. You might imagine crashing waves, but wave activity on Titan's seas is incredibly subtle. Research using Cassini data suggests tiny ripples, only a few millimeters to a couple of centimeters high, gently move across the seas. These gentle waves are a reflection of Titan's low gravity and dense atmosphere, which means you definitely wouldn't be catching any surf here. Enter Cassini, a bus-sized robot armed with radar eyes and a radio ear, slingshotting around Saturn for 13 years. Between 2004 and 2017, it flew past Titan 127 times, skimming so low it could taste the outer fringe of the moon's air. Each pass felt like a new chapter in a thriller. The radar maps showed seas and rivers, the cameras caught storm clouds blooming, the mass spectrometer sniffed organic goo. But the more data Cassini sent, the worse the methane budget looked. Every measurement said the same thing. Output far exceeds input. The books refused to balance. Cassini's suite of instruments was truly remarkable. Its radar instrument, specifically designed as the Titan radar mapper, was crucial for peering through Titan's thick, hazy atmosphere. It used synthetic aperture radar, or SAR, to map the surface, revealing lakes, mountains, and dunes, and could even detect how smooth or rough surfaces were, which was vital for studying Titan's methane seas. The Ion and Neutral Mass Spectrometer, or INMS, was another key player, designed to analyze the composition and structure of positive ions and neutral particles in Titan's upper atmosphere, giving us insights into its complex chemistry. Scientists tried every obvious fix. Maybe comets were dumping fresh methane. Not enough impacts to account for the sheer volume needed. Maybe the atmosphere recycled its own waste. The complex photochemistry in Titan's upper atmosphere, where sunlight breaks methane down, simply didn't support efficient recycling. Instead, it tends to create heavier hydrocarbons that rain down or form haze. Maybe underground reservoirs were venting. No direct vents were seen, making it hard to confirm this as the primary source. By 2012, the problem had a nickname inside mission control, as if the Titan methane crisis, as if the moon were a bank account bleeding dollars with no deposits. The crisis got so bad that one team jokingly proposed space whales, just to have something on the table. Everyone laughed, but the joke stung because no one had a better idea. The puzzle of the missing methane was a nagging question, undermining our understanding of this otherwise Earth-like world. Then, on flyby number 111, Cassini tried something new. Instead of just looking down, it looked sideways. Mission engineers flipped the spacecraft so its big, high-gain antenna pointed at Earth and its radio beam sliced through Titan's gravity field. The goal was to measure how the moon's mass bulged as Saturn tugged on it. The signal that came back was barely distorted. Milliseconds of delay, a Doppler wiggle smaller than a hummingbird's heartbeat, but it was enough. That tiny flex told a story. Titan's surface rises and falls by 10 meters every time it orbits Saturn. An ice shell sitting directly on rock can't bend that far, it would crack. The only way to get that much give is if the shell floats on something fluid, something denser than ice, but less dense than rock. The math pointed unequivocally to a global layer of liquid water salted with ammonia buried 50 to 100 kilometers down. This hidden ocean, estimated to be 50 to 100 kilometers deep and potentially containing more water than all of Earth's oceans combined, remains liquid despite the frigid temperatures because salts and ammonia act as a natural antifreeze. It's an incredible thought. A vast, salty ocean, completely cut off from the surface, sloshing under an ice crust that's probably 6 miles thick. Recent studies have even suggested that Titan's outer ice shell is quite complex, including a methane-rich crust layer up to 3 to 6 miles, or about 5 to 10 kilometers, thick, composed of methane clathrate ice. This clathrate crust acts as a crucial insulating layer, effectively warming the interior and influencing Titan's geological activity and, as we'll see, its persistent methane atmosphere. The presence of this subsurface ocean, detected through Cassini's precise gravity measurements, was a game-changer, fundamentally altering our understanding of Titan's interior. But how does a buried water ocean rescue a dying methane sky? The answer lies in a weird ice you can set on fire. Down where pressures reach 1,000 atmospheres, water molecules cage methane inside a crystal lattice, what chemists call a clathrate. Imagine a tiny molecular prison cell made of water ice holding a methane molecule captive. Cassini's gravity data hinted the base of Titan's ice shell is stuffed with these methane-rich ices. Over millions of years, Saturn's powerful tides don't just flex Titan's surface, they knead the entire ice shell, generating enough friction and heat to warm it. This subtle warming is just enough to crack those methane clathrate cages. Once freed, methane bubbles upward, percolating through fractures and fissures in the ice, slowly making its way to the base of the crust. From there, it can hitchhike on cryovolcanic slurries, think of them as icy, methane-rich lava flows, or simply seep straight through the ice until it erupts into the atmosphere as fresh gas. The moon literally burps its way out of bankruptcy. The numbers finally work. Release a few teragrams of methane per year, that's less than the weight of Lake Erie, and you can balance the photochemical drain. Cassini didn't see the vents directly. The plumes, if they exist, are hidden under Titan's omnipresent hydrocarbon smog. But the gravity data, the flex, the chemistry, and the missing methane all line up like planets in a rare conjunction. For the first time, the methane ledger balances to the penny. The discovery of this methane clathrate crust, estimated to be between 5 to 10 kilometers thick, not only explains the replenishment, but also how impact craters on Titan are much shallower than expected, as the clathrate ice warms the underlying ice shell, allowing it to relax and fill in craters over time. This mechanism helps explain why Titan, despite its age, has relatively few deep impact craters. Here's where the story tilts from neat accounting to profound. Titan now has two oceans, one on the surface of liquid methane and one underground of liquid water. These are two completely separate chemistries offering two potential incubators for life. Life on Earth needs water. Life on Titan, if it ever evolved, might sip methane instead. The discovery doesn't say life is there. It says the menu now offers two full courses. Astrobiologists call this a habitable duo, and it's unprecedented in the solar system. If either ocean spawned biology, Titan just became the most important petri dish beyond Earth. The implications for astrobiology are immense. The existence of these dual oceans expands our concept of habitable zones beyond just Earth-like conditions. Titan's environment, with its dense nitrogen atmosphere and methane cycle, shares some surprising similarities with early Earth, making it a natural laboratory to study prebiotic chemistry, the chemistry that precedes life. And speaking of chemistry, recent research from Chalmers University of Technology and NASA have revealed something truly astounding about Titan's unique chemical environment. They discovered that under Titan's extreme cold, substances that typically don't mix, like polar molecules such as hydrogen cyanide and non-polar hydrocarbons such as methane and ethane, can actually combine to form complex organic crystals. This discovery directly challenges the fundamental chemical rule that like dissolves like. These stable co-crystals, formed at temperatures near minus 180 degrees Celsius, could explain some of Titan's strange landscapes and provide new insights into how life's building blocks might have originated in such an exotic setting. NASA's upcoming Dragonfly mission, a nuclear-powered octocopter set to launch in 2027, will land near the equator and hop across the dunes looking for the chemical fingerprints of life. If it sniffs a surplus of acetylene or a deficit of hydrogen, we might be seeing the breath of microbes eking out a living in the clathrate slush or the surface liquids. Scientists like Chris McKay have theorized that a methane-based lifeform on Titan might consume hydrogen and acetylene similar to how life on Earth consumes oxygen. The observed lack of acetylene and downward flow of hydrogen from the atmosphere without a corresponding buildup on the surface are intriguing chemical anomalies that, while potentially explained by non-biological processes, leave open the door for biological activity. Even if the result is ambiguous, the mere possibility moves Titan from the fringe to the front row in the search for life. So the deepest secret of Titan isn't a single dramatic geyser or a buried artifact. It's a planetary recycling program billions of years old. A hidden water ocean, warmed by tides and laced with clathrates, steadily refills the moon's sky with methane, keeping the lakes liquid and the haze thick. Cassini's final gift was to show that the most alien place in our neighborhood runs on the same principle as Earth's life support systems: store, recycle, replenish. The discovery doesn't just solve a ledger problem, it fundamentally rewrites the rulebook for where biology might hide. 2 oceans, 1 moon, infinite possibilities. If you want to be among the first to see what Dragonfly finds, hit subscribe and ring the bell, because the next chapter of this mystery is about to take flight.